In today's lesson, we're going to continue talking about sampling distributions, and in particular, we're going to look at the distribution of the sample mean. What's really intriguing about the sample mean is that the sampling distribution is at least going to approximately always follow a normal distribution. Doesn't matter what our underlying data look like. If you take a large enough sample, the sample mean is going to behave as though it is normally distributed. And so this is a really powerful result. It's sort of a central theoretical result in statistics. And so we're going to take a look at that today. With today's lecture, the two main objectives are to be able to describe both the mean and the variance for the sampling distribution of the sample mean. And we should already be able to do this using the tools that we've talked about up till this point, but we'll look at that explicitly. And we also want to describe the limiting behavior for the sampling distribution of the sample mean. And so that limiting behavior is what I was just alluding to, where as the sample size continues to grow, everything's going to behave as though it's normally distributed. So by way of example, we could start thinking about some sort of production facility. So this image here is a image from the production of soda streams. And you could think about a similar technique being applied to any manufacturing situation. We know that sort of the average shift is going to have some variability in how much is produced, how much product is made, right? Because workers are going to be slightly different in their productivity levels. Perhaps someone is off sick, right? We're going to have some variability around what people are able to do. But on average, knowing how much can be produced in a single shift is important in order to be able to plan our stock levels, to be able to plan what we can sell, to be able to sort of just plan the business into the future. And so when we start thinking about this average, how much is produced on average, we want to be able to quantify how uncertain we are about that average in order to be able to make sure that if we have a few bad shifts in a row where we're producing less than, or if we have a few very productive shifts, that whatever planning we've put in place is going to be able to accommodate that. And we'll want to be able to accommodate that with some certainty that sort of no matter what outcome happens, we're going to be ready for it. Right? And so understanding how sample means are distributed is important in its own regard, and then it's something that we're going to use more and more down the road in this course. So to sort of set up what we're considering today, take x bar to represent the random variable for the sample mean. So we're not thinking about having a specific sample, but if I were to collect endpoints and then compute their average, then the x bar with the capital X represents what that average is going to be. So it's still random because we don't have any data yet. Now, regardless of the true distribution, the following are going to always hold. The expected value of x bar is always going to be the expected value of x, which we can just call mu, right? And we've seen this before. We can also write down that the variance of x bar, in this case, should say the variance of x bar is going to equal 1 over n times the variance of x, which we can just denote as sigma squared over n. Now, in order for this to be true, we require the sample to be independent of one another, but we're always assuming that in this course. And so we can write down that the variance is going to be sigma squared over n. Now, often we're going to be looking at the standard deviation of the sample mean, and we give this one a special name. We call it the standard error. And if you just take the square root of the variance, we're going to get sigma over the square root of n, right? And so again, these things hold true no matter what the distribution of the data is. This is just a simple application of the properties of expectation and of variance. Now, if instead of considering the sample means, we considered the totals, which is something that we might want to do sometimes, you can sort of multiply through by n here, right? And so when you multiply the expectation by n, constants just simply multiply the expectation, so we get n mu. And when you multiply our variance by a constant, you pull it out squared, right? And so you're going to get n squared times sigma squared over n, which is just going to be n sigma squared. Okay, so all of these properties are going to hold simply because of the expectation or the variance, not specific to the distribution we're working with. Now, the sample mean is always going to have the same expectation as the underlying mean, right? Doesn't matter how big your sample is, doesn't matter what distribution you're drawing from. If you compute the sample mean and you think about that as a random quantity, that random quantity is always going to be centered at the exact same place that the underlying distribution is centered at. We also saw that the variance is going to be scaled down by n, right? So it's going to be sigma squared over n. And so as the sample size grows, the variance is going to shrink to be 0, right? If you think about the difference between taking a sample size 10 and a sample of size 10 million, well, your variance is going to be 1/1,000,000th of the size if you have sort of 1,000,000 times more observations, right? And so you can imagine taking that even larger, and eventually the variance is going to be so close to 0 that it may as well be 0, right? And as the variance of any random quantity shrinks towards 0, that quantity has less and less spread in it, right? We're remembering that the variance is a measure of how spread out the random variable is. And in particular, in order to have 0 variance, we have to have something which is constant, right? And so if you could imagine taking an infinite sample here, well, we know it's going to be centered on the mean, and if its variance is equal to 0, well, then it has to constantly be the mean, which means that in infinitely sized samples, we're always going to get exactly the sample mean. And so in practice, we're never going to have infinitely sized samples, but the fact that larger and larger samples shrink the variance more and more means that as the sample size ends up growing, the amount of spread we can view on our sample mean is going to continue to shrink. So if we were to assume that the underlying distribution was normal with mean sigma squared, or mean mu, variance sigma squared, then the sample mean is also going to be exactly normally distributed. Okay, so everything we've seen up till this point is going to not depend on the underlying distribution. But if we say that the underlying distribution is normal, then the sample mean will be exactly normal. However, because of this sort of result about this shrinking variance, even if the underlying data are non-normal, the sample mean is not going to be exactly normal. However, it's going to act as though it were normal if our sample size is large enough, right? So what we have going on here is that the sample mean is always going to have expectation equal to the underlying mean from the distribution. It's always going to have variance given by sigma squared divided by n. And so we can see that it's always going to end up being centered on the true sample mean with smaller and smaller spread around it as the sample size grows. In terms of what that distribution actually looks like, if the data are normally distributed to begin, then the sample mean is going to be normally distributed no matter the sample size. If the data are not normally distributed to begin, then as long as our sample size is getting big enough, then it's going to behave as though it is normally distributed. That result about behaving as though it's normally distributed is a result we call the central limit theorem. And it's one of the most important results in statistics. And it simply says that as you increase your sample size more and more, the sample mean is going to behave as though it came from a normal distribution. So, in summary, sample mean has a distribution with expectation equal to the underlying distribution's expectation, and its variance is going to 0 in n. So we're going to become centered right on the true mean. Normal samples will have exactly normal sampling distributions. And if you have a non-normal sample, well, it's going to be approximately normally distributed once you take a large enough sample size. Now, the question might be, what is a large enough sample size? We'll talk a little bit about this throughout the course. I don't think that there's a great set value to look at. The idea is essentially, if you're taking enough people, you can start to use this as your result. So in the coming lectures, we're going to continue looking at statistical estimation and thinking about sampling distributions, and I hope to see all of you in those lessons.